Here's a sentence. The mother of the singer of Superstition is. Pause and notice what your brain just did. You didn't jump straight to an answer. First you worked out who sings Superstition, that's Stevie Wonder, and only then did you go looking for his mother. 2 steps chained together with the middle one entirely in your head. Now a language model given that same prompt will produce an answer in a single forward pass. So here's the question this Google DeepMind paper asks. Does the model also silently work out that middle step, quietly thinking Stevie Wonder along the way? Or is it doing something else entirely? The key word here is latent. Models can chain reasoning when you let them write it out. That's what chain of thought prompting does. The steps appear in the text, and we know they can reason over facts given the prompt. But this is different and harder. Nothing in the input says Stevie Wonder. The bridge has to be constructed internally, from the model's own stored knowledge, inside a single pass, and then used with no external scratchpad at all. That's latent multi-hop reasoning, and whether it genuinely happens has been surprisingly hard to establish. And the answer matters quite a bit in a practical way. If models really do compose facts internally, then their knowledge is genuinely modular. Facts can be chained into conclusions the model was never explicitly taught, and if you correct one underlying fact, everything downstream should update with it. If instead they're pattern-matching 2-hop questions they've effectively seen before, then they'll break on novel combinations, and fixing a fact won't propagate. It's the difference between a model that knows things and a model that has memorized answers. So the researchers set out to measure it directly. Let's name the pieces. That hidden middle step, Stevie Wonder, is called the bridge entity, because it bridges the 2 halves of the question. So the reasoning pathway splits cleanly into 2 hops. Hop 1, take the descriptive phrase, the singer of Superstition, and internally resolve it to the actual entity, Stevie Wonder. Hop 2, take that entity and retrieve the requested attribute, his mother, to complete the sentence. The beauty of splitting it this way is that each hop can now be tested separately, with its own experiment, and critically, both have to work for the whole chain to count. So how do you test whether hop 1 happens inside a network? The researchers measure something they call entity recall, essentially how strongly the model's internal states light up with Stevie Wonder, while it's processing the prompt, even though his name never appears. But a raw measurement isn't enough, you need a controlled comparison. So they change the clue. They swap Superstition for Thriller, which points at Michael Jackson instead. If the model is genuinely doing hop 1, then internal recall of the correct bridge entity should rise specifically when the clue points to that entity. It's a clean causal manipulation. And the results are quite convincing. Across the layers of the network, the frequency with which changing the clue increases recall of the right bridge entity sits well above chance, and it climbs steadily with depth, peaking in the later middle layers, around 0.71 for a Llama 27b. They also run the same test by substituting the relation instead of the entity, and see a similar, slightly noisier pattern. Even better, when they break it down by type of fact, strong first-hop evidence appears in up to 73% of the fact composition types they tested. The model really is forming that hidden middle step. Hop 1 is only half the story, though. Forming the thought Stevie Wonder is useless if the model doesn't then USE it. So how do you test the second hop? The trick here is elegant. Take the model's answer to the hard 2-hop prompt, and compare it to its answer to the easy direct prompt, the mother of Stevie Wonder is. Call the similarity between those 2 answers consistency. Now the question becomes causal. When the model internally recalls the bridge entity more strongly, do those 2 answers become more consistent? If yes, the recalled entity is genuinely driving the final output. Here the story gets more complicated and more interesting. The effect is real. Stronger bridge entity recall does push the 2 answers into better agreement, so the second hop does happen. But it's noticeably weaker than the first hop, and look at how much it varies across the panels. For some kinds of facts, like the mother of a song's singer, the effect is robust across most layers. For others, like the founder of a person's undergraduate university, it's patchy, with plenty of layers showing no effect at all. The utilization is highly contextual. It depends a lot on what you're asking about. It's worth pausing on the scale of the evaluation. because it's what makes the conclusions trustworthy. They built a dedicated dataset called TwoHopFact, with more than 45,000 two-hop prompts spanning 52 different fact composition types, things like the mother of the singer of a song, or the president of the country whose anthem is a given piece. That variety is essential, because as we just saw, the effect depends heavily on the type of relation. And they ran everything across LLM-2 at 3 sizes, 7 billion, 13 billion, and 70 billion parameters, which sets up the most striking finding of the paper. That finding is about scale, and it's genuinely surprising. For the first hop, bigger is clearly better. The evidence strengthens as models grow, from 0.71 at 7 billion to 0.22 at 13 billion to 0.78 at 70 billion. A nice, clean upward trend, exactly what you'd hope for. But the second hop shows no such trend. It stays essentially flat as the model grows, and by some measures it even dips slightly. So the ability to form the hidden intermediate thought improves with scale, while the ability to actually use it does not. Just building bigger models may not fix composition. Of course, what we ultimately care about is the full pathway, both hops firing on the same prompt. When they measure that jointly, the picture is nuanced. For certain relation types, the complete reasoning pathway shows up in more than 80% of prompts, which is genuinely strong evidence of latent multi-hop reasoning happening. But averaged across all the fact types, the evidence for the full traversal is only moderate. So the honest summary is, latent multi-hop reasoning is definitely real, and sometimes it's the dominant mode, but it is not yet a reliable, universal capability you can count on. One of the nicer details is the layer structure, because it tells a story about the order of operations inside the model. Evidence for the first hop is weak in the early layers and grows steadily with depth, becoming clearest in the later middle layers. That makes sense. The model needs to read the descriptive phrase, gather it up, and resolve it, which takes some processing before the bridge entity can crystallize. And the second hop's effect tends to appear in a similar middle band, consistent with the picture that the entity is formed first, then queried. This lines up neatly with other interpretability work showing that mid-layer, feed-forward modules are where factual lookups happen. A result like this lives or dies on its controls, and the researchers are careful here. The obvious worry is that these correlations are artifacts, that any change to the prompt would shift the internals, and you'd see a similar pattern from nothing but noise. So they run comparisons against randomized versions of the model, where the pattern should vanish, and it does. They vary how prompts are phrased, to check that the effect isn't an artifact of one particular wording. And they test both substituting the entity and substituting the relation, two independent ways of changing the clue, and get consistent stories from both. The effect survives the scrutiny. Let me put the whole answer in one place. Does an LLM latently perform multi-hop reasoning? A qualified yes. Hop 1, forming the bridge entity internally, is well supported and gets better with scale. Hop 2, actually using that entity to produce the answer, is real but weaker and depends heavily on the kind of fact. And putting both together on the same prompt is common for some relation types and uncommon for others. The models are doing more genuine internal reasoning than skeptics assumed, and less reliable reasoning than optimists hoped. Both halves of that sentence matter. So what should we carry away from this? First, a real result about machine cognition. These models do construct hidden intermediate thoughts. Given a description, they silently resolve it to an entity with no prompting to do so. That's a meaningful form of internal reasoning. Second, a clear-eyed view of the limits. The weak link isn't forming the thought, it's using it, and scale alone hasn't fixed that. This helps explain a familiar frustration. A model that clearly knows two separate facts, yet fumbles the question that requires joining them. And third, a practical implication for knowledge editing. If you correct a fact, don't assume everything downstream updates. The chain is real, but it is not yet strong. Thanks for watching.